Hello, and welcome to our talk, Efficient Proximal Mapping of the One-Path Norm Regularizer of Shallow Networks. This is joint work with my colleagues Paul Roland, Nadav Halak, and Volkan Jever. Let's talk about what is the path norm and what is so interesting about it. In the context of supervised learning, the goal is to obtain a low misclassification error, and one important component is the so-called generalization gap, the difference between the error on the training set and the true error, usually measured using some independent test set. Researchers are interested in deriving complexity measures of the learned function that explains such generalization gap. The path norm is precisely one such measure of complexity that can be computed from the weights of a neural network. In a large-scale experimental study, it has been found to be positively correlated with the generalization gap, and more so than other rival complexity measures, like the Frobenius norm, distance to initialization, or the spectral bound. It is unnatural to use it as a regularization term during training. However, two crucial questions arise. First, is the path norm also related to how robust is the network to adversarial perturbations? And second, how do we optimize the regularized objective using the path norm? Our contributions in this work are the following. We show that the one-path norm also provides robustness to an infinity adversarial perturbations by relating it to the Lipschitz constant of the network. We derive an efficient proximal mapping of the so-called one-path norm of shallow, single hidden layer networks, enabling proximal gradient type methods to minimize the non-convex, non-smooth objective. Finally, we illustrate our findings experimentally. So what exactly is the path norm? We will focus on a particular variant, the one-path norm. It is defined as follows. So for a feed-forward network, we consider all paths from input to output in its computation graph. Each edge corresponds to an entry in some weight matrix. For each such path, we take the absolute value of the product of weights along the path, and finally, we sum all such values. For a shallow network with weight matrices V and W, we will denote the one-path norm as P1 V, W. Now, let's discuss what is the relation of the one-path norm and the robustness of the network to an infinity adversarial perturbations. In this context, we want to obtain a certificate that a bounded perturbation of the input cannot change the output of the network. One well-known such certificate is the Lipschitz constant of the network, and we know that lower values of such constant imply that the perturbation needed to change the label is much larger. Precisely, we find the following. First, equation 3 states that the one-path norm of the subnetwork corresponding to each output upper bounds the infinite Lipschitz constant of the subnetwork. The bound that we obtain in this way is better than the trivial bound that we can obtain by multiplying layer-wise matrix norms. Then, equation 4 states that the one-path norm upper bounds the Lipschitz constant of the network when the norm in the input is the infinity norm and the norm in the output is the L1 norm. Again, the bound is better than the layer-wise product bound. We conclude that it is desirable to regularize using the one-path norm to obtain both a low generalization gap and robustness to perturbations. But how do we optimize the objective? Let's take a look at it. This is a composite non-convex problem. The first part is a typical loss in the form of an expectation, which we assume is differentiable. It suffices to use differentiable activation functions in the network. The second part is the one-path norm, which is non-convex and non-smooth. The naive approach would be to just use automatic differentiation on PyTorch or TensorFlow. But this has the drawback that first, we might be computing erroneous gradients, and second, there are no guarantees that we will even find a stationary point in such way. In contrast, if we use a proximal gradient descent algorithm, we completely avoid erroneous gradients because we only need the gradient for the differentiable part. And second, we have guarantees that we converge at least to a stationary point. Now on to deriving a proximal gradient descent algorithm. We will only consider here the single output scenario, where the neural network only outputs a scalar. The multi-output case can be found in the paper. So in order to use our proximal gradient descent, what we need is to provide a way to efficiently compute the proximal map of the one-path norm regularizer term. By definition, this proximal map is given by equation 5. Although this is a non-convex problem, it can be shown to have a global optimal solution. The first step to derive an efficient algorithm to solve this problem is to observe that it is separable with respect to the ith coordinate of V and the ith row of W. So it is enough to solve the reduced problem in equation 6 once per hidden neuron. A final simplification of the problem is to notice that the signs of the optimal solution can be determined by the signs of the arguments x and y. We can thus restrict all decision variables to be non-negative, and we add the signs at the end to obtain the solution of the initial problem. For example, this is really similar to the derivation of the proximal mapping of the L1 norm. So this is the final form of the problem that we will study. As a function of v and w, this function is differentiable. So the first step is to derive the first order optimality conditions. From these conditions, we can easily observe that the optimal vector w star is ordered in the same way as the input vector y, since the term minus lambda v star is the same for all coordinates. As w is constrained to be non-negative, it follows that if some coordinate of the I of w is 0, then all other coordinates of w corresponding to smaller values of y must also be 0. This also means that the non-zero elements of w star will be the coordinates associated with the largest entries of y in magnitude. Since the regularizer is invariant under permutation of the coordinates of w, we can assume that the input vector y is sorted in decreasing magnitude order, so that the non-zero entries of w are only the first ones. As we will see, this property will allow us to list all first-order stationary points based on the number of non-zero elements of w. The key ingredient for computing the proximal mapping is to observe that all first-order stationary points can be indexed by an integer s, representing the number of non-zero elements of the vector w. After some algebra, it is possible to compute a closed-form solution for the stationary point associated with each integer s. Note that some of these pairs may not be feasible, meaning that they can give negative values. In that case, there is no stationary point for this particular value of s. Since s is between 0 and m, the number of hidden neurons, it means that there are at most m first-order stationary points that can all be computed in closed form. This already gives an efficient algorithm for computing the proximal by computing all feasible stationary points and returning the one that yields the smallest objective value. But in fact, we can do better. We can actually make the computation faster by noting the following. First, the number of non-zero elements of w star is upper bounded by 1 over lambda squared, where lambda is the regularization parameter. We obtained this result from the second order optimality conditions. This allows us to look only on a restricted range of values of s when computing the proximal map. Second, we notice that the objective function h lambda is monotonically decreasing when we increase s, and thus, the larger s, the better. This provides a way to directly compute the optimal value of s by just searching for the largest s that corresponds to a feasible stationary point. This last operation can be efficiently performed using a binary search. So, to summarize, we start by sorting the input vector y, while storing the applied permutation. We then search for the optimal integer s using binary search and compute the associated stationary point. Finally, we apply the inverse permutation and multiply the solution by the sign of the input parameters. The complexity of this algorithm is linear in the size of y. However, we must perform this procedure for each hidden neuron. There are m hidden neurons, so the total complexity of the proximal map computation is O order of n times m, where n is the size of the input. This is the same complexity as backpropagation. Now on to some experiments. We compare SGD with constant step size and proximal SGD with constant step size. We train shallow networks with cross-entropy loss, and we observe, as expected, that the prox SGD consistently achieves lower values of the objective function. In this case, automatic subdifferentiation is just not appropriate. It is not a good choice. We also compare how the regularization parameter affects the error and robust error of a classifier. We find that one path norm is more efficient at trading off accuracy for robustness than L1 regularization. This means that for some regularization parameter lambda, one path norm is able to obtain the same accuracy but more robustness. In these datasets, we find that path norm is only similar or slightly better than layer-wise regularization. So to conclude, 1. Path norm promotes not only good generalization, but also robustness. 2. We should use prox SGD to train shallow networks with one path norm regularization. And 3. The proximal mapping for arbitrary deep networks is much more complicated. The first and second order stationarity conditions become much more difficult to handle. This can be an interesting avenue for future research. Thank you for your attention.